Today, we're diving into the fascinating world of mechatronics engineering. Have you ever wondered how modern cars can automatically brake to prevent accidents, or how a smart thermostat knows exactly when to adjust your home's temperature? These marvels are all thanks to mechatronics. In this introduction to mechatronics, we'll explore what it is, a bit of how it came to be, the real-world applications that surround us, the skills and tools mechatronics engineers use, the diverse career paths available, and even what the future holds for this exciting field. Mechatronics is all about synergy. It's where mechanical engineering, electronics, and computer control meet and work together. Instead of thinking of these as separate areas, mechatronics combines them into one integrated approach. The result? Smart machines and devices that can sense their environment, make decisions, and act on the world. It's an interdisciplinary field by nature. Imagine a robot or an automatic car. It has mechanical parts, electronic components, and a computer brain with software making everything work together. That blend is exactly what mechatronics is about. What is mechatronics? In simple terms, mechatronics means combining mechanics and electronics. In fact, the word itself is a mashup of mechanics and electronics. The term was famously coined in the late 1960s by a Japanese engineer named Tetsuro Mori of Yaskawa Electric Corporation. Yaskawa even trademarked mechatronics in 1971, before eventually letting other companies and engineers use it freely. Back then, the idea was just to describe machines that had both mechanical and electrical components, like automated factory machines. But as technology advanced, mechatronics expanded to include computers, software, and control systems as well. So, what does a mechatronic system look like? Think of a basic example, an automatic door. It has mechanical parts, electronic sensors, and a controller to decide when to open or close the door. All three parts work together seamlessly. The mechatronics approach is designing such systems holistically. The mechanical design, the electronics, and the programming are all considered from the start to create a better product. By uniting these disciplines, mechatronics engineers create systems that are simpler, more efficient, and more reliable than if you design the mechanical and electronic aspects separately. A brief history of mechatronics. Let's step back for a moment. How did mechatronics originate? As mentioned, it began in Japan around 1969 when Tetsuro Mori first used the term. Early mechatronics in the 1970s might have been as simple as adding electronic controls to mechanical factory equipment, for instance, using electronics to control a machine tool's operation precisely. In the 1980s, things really took off with the advent of affordable microprocessors and computers. Suddenly, we could put small computers into machines, dramatically improving their capabilities and performance. By the 1990s, advances in software and artificial intelligence, sometimes called computational intelligence, were being applied to mechatronic systems, which revolutionized the field. Machines could now not only follow predetermined instructions, but also adapt, learn, and make smarter decisions. Over time, mechatronics has grown from a niche term to a mainstream concept in engineering worldwide. Once Yaskawa Electric released the trademark, the word mechatronics quickly spread into many languages and became an essential term in advanced technology and industry. Today, mechatronics is often seen as synonymous with automation, robotics, and electromechanical engineering. Pretty much any modern system where mechanical parts and electronics interact in an intelligent way can be called a mechatronic system. Real-world applications of mechatronics. One of the coolest things about mechatronics is that it's everywhere around us, often hidden in plain sight. Let's look at some real-world applications and examples, including areas you might not initially suspect. Automotive and transportation. Modern vehicles are packed with mechatronic systems. For example, the anti-lock braking system in your car is a classic mechatronic system. It uses wheel speed sensors and a control unit to modulate brake pressure via hydraulic actuators so your car can stop safely without skidding. Cruise control is another. It automatically adjusts the throttle to maintain your speed, again closing the loop between mechanical action and electronic sensing. Today's cars, especially hybrids and electric vehicles, have dozens of these smart features working together. Even something like the deployment of airbags involves mechatronics. Sensors detect a collision and trigger mechanical actuators to inflate the bag. In aerospace, the stakes are even higher. Airplanes rely on mechatronic systems for flight control and navigation, blending mechanical controls with electronic sensors to keep flight stable and safe. Industrial automation and robotics. If you walk into a modern manufacturing plant, you'll see robots and automated machines assembling products with minimal human input. Those industrial robots on assembly lines, like the ones that weld and put together cars in factories, are prime examples of mechatronics at work. They involve mechanical arms, electronic sensors and motors, and are all orchestrated by computer programs. Mechatronics has allowed us to create smart factories with machines that can operate 24/7, performing tasks from precise welding to packaging. This also includes things like conveyor systems with sensors and feedback loops to sort items, or quality control systems that use cameras to inspect products and automatically reject defects. Essentially, mechatronics is the backbone of Industry 4.0, the new wave of industry that uses automation, data exchange, and cyber-physical systems to optimize manufacturing. Healthcare and medical devices. Perhaps one of the most life-changing applications of mechatronics is in healthcare. Medical mechatronics is enabling advanced devices that improve or save lives. Consider robotic surgical systems like the famous Da Vinci surgical system, a multi-arm robot that a surgeon controls to perform minimally invasive surgeries with extreme precision. That's a mechatronic marvel. It has mechanical robotic arms, high-definition cameras and sensors, and a sophisticated computer interface translating the surgeon's hand movements into tiny, precise motions of surgical instruments. Another example is prosthetic limbs. Modern prosthetic arms and legs often have electronic sensors and motors controlled by microprocessors, allowing them to move more naturally. Some even respond to electrical signals from the user's muscles or nerves. This synergy of mechanical parts with electronics and software is classic mechatronics. Beyond that, think of devices like insulin pumps, pacemakers, or MRI machines. They all involve mechanical components precisely guided by electronics and software to deliver medical therapy or imaging. Mechatronics is also key in developing assistive technologies. For example, powered exoskeleton suits that help patients with spinal injuries walk again by using robotic leg supports. In short, many medical devices and equipment are essentially mechatronic systems designed to be safe, reliable, and accurate. Smart homes and consumer gadgets. When it comes to daily life, mechatronics is what makes our homes and gadgets smart. A smart home is basically a network of mechatronic subsystems working together: thermostats that detect temperature and mechanically adjust your heating/cooling, automated door locks and security cameras, motorized blinds that open or close based on sunlight, and so on. For instance, a smart thermostat like the Nest uses temperature sensors and motion detectors plus a motor to control the HVAC system, all managed by software that learns your schedule. Robotic vacuum cleaners are another great example. They move around while using sensors to map your house and avoid obstacles, guided by control algorithms that tell them where to clean. Even kitchen appliances have gotten smart. Your washing machine might adjust its drum motion and water usage based on the load, using sensors and control software. The goal of these home mechatronic systems is often convenience and efficiency: lights that turn off when nobody's in the room, or sprinklers that adjust to weather automatically, all of which reduce waste and make life easier. In fact, a fully integrated smart home, sometimes called a home automation system, is considered one of the best examples of mechatronics in action. Consumer electronics. Our personal gadgets also rely on mechatronics. Consider your smartphone. It may not have obvious moving parts like a robot, but it's packed with sensors and actuators. When you use your phone's camera and it autofocuses or stabilizes an image, that's a mechatronic mechanism at work, like a micro motor moving the lens based on sensor feedback. Video game controllers buzz or trigger resistance to simulate feedback, like a car steering wheel that fights you in a racing game. Again, small motors controlled by software. Digital cameras adjust lenses and aperture using mechatronic systems. Even something as simple as a printer is mechatronic. Mechanical rollers and print heads precisely controlled by electronics and software to put ink on paper. In short, many everyday consumer products, from autofocus cameras to smartphones, came out of advancements in sensors, microcontrollers, and actuators developed in the field of mechatronics. Those are just a few areas. Mechatronics also plays a role in agriculture, entertainment, and much more. The key point is that mechatronics engineers build systems that are all around us, making devices smarter, faster, and more reliable. Technical skills and tools in mechatronics. Because mechatronics is so broad, mechatronics engineers end up wearing many hats. They need a mix of mechanical know-how, electrical/electronic skills, and programming ability. Let's break down some of the key technical skills and tools that are common in this field. Mechanical design using CAD. Mechatronics engineers often start by designing mechanical components or systems, and for that they use CAD, computer-aided design, software. Tools like SolidWorks, AutoCAD, or Fusion 360 allow them to create 3D models of parts, whether it's a robot arm or a gear assembly. Knowing how to design for durability and functionality is crucial. Often, CAD goes hand in hand with CAM, computer-aided manufacturing, to actually produce prototypes. In essence, strong mechanical engineering fundamentals, like understanding dynamics, materials, and how mechanisms work, are needed to build the physical side of a mechatronic system. Fun fact, many mechanical systems today are first virtually prototyped in CAD to catch issues early, a skill that's considered essential in mechatronics. Electronics and circuitry. A mechatronics engineer also needs to be comfortable with circuits. After all, they'll be working with sensors, motors, and microcontrollers. This includes understanding how to read circuit schematics, use tools like oscilloscopes, and design or at least integrate basic electronic components. They might work with microcontrollers or microprocessors like an Arduino or Raspberry Pi to serve as the brain of a device, reading inputs from sensors and sending signals to actuators. Knowledge of power electronics, and of analog sensors all come into play. They must ensure that the hardware can reliably sense and control the mechanical parts. Programming and software. Coding is a huge part of modern mechatronics. To control a system, you often program the logic that decides how it behaves. This can range from writing embedded C code on a microcontroller, to scripting in Python for data analysis, to designing a user interface on a PC that communicates with your device. PLC programming, programmable logic controllers, is particularly important in industrial settings. PLCs are rugged computers used in factories to run machines. Think of them as the workhorses that control conveyor belts, motors, and switches on an assembly line. A mechatronics engineer might program a PLC using ladder logic or other languages to sequence operations for automated equipment. Outside of PLCs, common languages include C++ and Python. C++ is popular for performance-critical control software, and Python for quick prototyping or data handling. There's also specialized robotics programming, like ROS, the Robot Operating System, or even proprietary robot programming languages, for those working in robotics. The bottom line, software brings intelligence to mechanical systems, so mechatronics folks need to be quite versatile in coding at various levels. Control systems and MATLAB/Simulink. Designing how a system behaves often involves control theory, figuring out how to make a machine follow a desired command accurately and stably. For example, if you want a drone to hover at a certain altitude, you need a control system reading the altitude sensor and adjusting the propellers. Many mechatronics engineers use tools like MATLAB and Simulink for this kind of work. MATLAB is a programming and numeric computing platform that's great for analyzing data, modeling systems, and designing controllers. Simulink is a companion tool that lets you simulate dynamic systems with block diagrams. You can model a mechanical system, like a spring damper or a robot joint, and then simulate how it responds to a control algorithm. These tools allow engineers to prototype and test control strategies virtually before trying them on real hardware. In fact, being able to simulate a mechatronic system can save a lot of time and prevent damage to actual equipment. Beyond MATLAB, there are other simulation tools, like LabVIEW, or specialized software for circuit simulation, but MATLAB/Simulink is very commonly taught and used in the field. Hands-on building and testing. Apart from computer-based tools, mechatronics engineers also spend time in the lab or workshop. They might be soldering circuits, building prototypes with 3D printed parts, or debugging why a sensor isn't reading correctly. Skills in using basic workshop tools, understanding schematics, and system-level troubleshooting are key. Often they use test equipment like multimeters or logic analyzers to track down problems. Being able to move seamlessly from theory/design to practical implementation sets mechatronics apart. You need both sets of skills. In summary, a mechatronics engineer is a bit of a jack of all trades. They might start the day tweaking a 3D CAD model, then spend the afternoon programming a microcontroller, and end by testing everything on the actual machine. This blend of skills is what makes the job exciting and ensures that mechatronics engineers can integrate all the pieces together into a working whole. Careers and industries in mechatronics. Because mechatronics covers such a broad skill set, it opens doors to a wide range of career paths and industries. Essentially, any industry that designs or uses smart machines is a place for mechatronics engineers. Here are some of the prominent sectors and roles. Manufacturing and automation. Many mechatronics graduates work in factories or in designing automation equipment. Job titles like automation engineer, control systems engineer, or robotics engineer are common. In these roles, you might be programming robotic arms, designing automated production lines, or maintaining systems that keep factories running efficiently. Industries like electronics manufacturing, food processing, or logistics, think automated warehouses, all need these skills to improve productivity. Automotive. The automotive industry is a major employer of mechatronics engineers. Modern cars and trucks rely on numerous electronic control units and sophisticated mechatronic systems like engine control, braking, infotainment systems, driver assistance features, etc. As a mechatronics engineer in this field, you might work on developing new features for vehicles, for example, working on sensors and control algorithms for self-driving cars, or improving electric vehicle battery management systems. Automotive roles could be in big car companies or in the many suppliers that make car components, like Bosch, Continental, etc., which design everything from airbag controllers to adaptive headlights. With the rise of electric and autonomous vehicles, there's a huge demand for engineers who understand the intersection of mechanics, electronics, and software. Aerospace and defense. Aerospace companies, like Boeing, SpaceX, or NASA contractors, need mechatronics expertise to design complex systems such as aircraft controls, satellite mechanisms, or drones. For instance, an avionics engineer is dealing with the mechatronics on a plane, flight control computers, navigation systems, and the electromechanical components that move wings and rudders. Similarly, in the space sector, everything from a Mars rover to a satellite deployment mechanism involves mechatronics. Defense industry projects might include autonomous vehicles or robotic systems for surveillance and reconnaissance. If you love the idea of working on cutting-edge technology like rockets or robotic space explorers, mechatronics is a great foundation. Healthcare and biomedical. As we discussed in the applications, healthcare is becoming increasingly high-tech with mechatronic devices. Career paths here include working for companies that design medical robots, diagnostic machines, or high-end hospital equipment. You could be a biomedical engineer with a mechatronics background, developing the next-gen prosthetic arm or improving robotic surgery tools. There are also roles in research institutions or hospitals to maintain and innovate medical equipment. The combination of mechatronics with biotechnology is a growing niche, like designing machines that interface with the human body. It's a field where you can really make a difference in people's lives through engineering. Consumer electronics and IoT, tech companies that make gadgets, appliances, or any smart consumer devices also hire mechatronics engineers. For example, working at a company that designs smart home devices, you could be developing a new smart refrigerator that has sensors to adjust cooling, or a home security drone. Roles could be in product design or testing, ensuring that the hardware and software in a gadget work together seamlessly. The rise of IoT, the Internet of Things, everyday objects being embedded with sensors and connectivity, means mechatronics folks are needed to build those smart versions of traditional products. Everything from smart thermostats to wearable health trackers involve integration of hardware and software, which is right up the alley of mechatronics engineering. Research and development. Some mechatronics graduates go into R&D, either in academia or in corporate R&D labs. Because mechatronics is at the intersection of several fields, R&D can be very exciting. You might work on advanced robotics, autonomous systems, or new types of sensors/actuators. For example, developing a new robotic hand that can delicately pick up any object, or researching how to improve drone flight stability using AI algorithms. Universities and national labs often look for people with interdisciplinary skills to push the boundaries of what robots and machines can do. The salary and demand can be quite good, as industries are eager for engineers who can do it all. Mechatronics professionals find opportunities in sectors ranging from automotive and manufacturing to healthcare, agriculture, IT, and aerospace. The versatility is a big plus. It means as a mechatronics engineer, you could pivot between industries. If cars don't excite you, maybe you apply your skills in the renewable energy sector, like designing smart wind turbines or solar panel cleaning robots, for instance. Or maybe you start your own startup, creating a new gadget that could become the next big thing in consumer tech. The possibilities are broad, because as technology evolves, the need for integrative engineering only grows. Emerging trends and future directions. What does the future hold for mechatronics? In a word, innovation. This field sits at the heart of technological innovation, and several exciting trends are shaping its future. Artificial intelligence and machine learning. We're seeing AI increasingly woven into mechatronic systems. This means machines aren't just following pre-programmed rules, they're learning from data and improving their performance. For example, an AI-powered robot can learn to pick up new objects by itself or optimize how it walks based on experience. Machine learning algorithms can tune control systems better than a human engineer in some cases, by processing tons of sensor data and finding patterns. A great real-world example is predictive maintenance. AI can monitor data from machines, vibrations, temperature, etc., and predict when a part might fail, so it can be replaced beforehand. This keeps factories running smoothly with less downtime. Another example is autonomous vehicles. Self-driving cars use AI to interpret sensor data, like camera and radar inputs, and make driving decisions. In short, AI and mechatronics together create intelligent, autonomous systems that can adapt to new situations, rather than just repeating a fixed set of actions. Internet of Things, IoT, and connectivity. As mentioned, IoT is connecting devices across the globe. For mechatronics, this means your machines can talk to each other and to the cloud. Imagine a network of sensors on a farm automatically controlling irrigation, or a smart home where all appliances communicate to optimize energy use. IoT allows for real-time monitoring and remote control of mechatronic systems. A technician might get an alert on their phone if a machine in a factory half a world away is having an issue. Or a doctor might remotely monitor a patient's implanted device. This connectivity also enables collecting big data from devices to analyze and improve them. Many of the smart components in IoT devices are essentially mechatronic subsystems. They have physical sensors/actuators plus connectivity. As IoT expands, mechatronics engineers are key in ensuring all these connected gadgets are designed securely and work reliably over networks. Cyber physical systems and Industry 4.0. You might have heard the buzzword Industry 4.0, which is like the next industrial revolution. At its core are cyber physical systems, a fancy term for deeply integrating computation with physical processes. In other words, machines, sensors, and computers are all intertwined in industrial environments. Mechatronics is essential here, since it's literally about blending the physical and digital. In a smart factory, you might have sensors on every machine sending data to a central AI that optimizes the whole production line on the fly. If something goes wrong, the system can adjust or even reconfigure robots to handle changes. Digital twins are another emerging idea. That's where you have a virtual model of a physical system, say, a whole factory or a turbine, that runs in parallel, helping to simulate and predict performance. Mechatronics provides the real-world data and models that feed into these digital twins. Essentially, by enabling the creation of sophisticated cyber-physical systems, mechatronics is helping optimize production processes and usher in more flexible, efficient manufacturing. Robotics everywhere. The field of robotics is actually considered a subset of mechatronics, since a robot is the ultimate combo of mechanisms, electronics, and software. We can expect to see robots more and more in everyday life, not just in factories. Collaborative robots, cobots, are a trend in industry. These are robots designed to work safely alongside humans on tasks, blending human flexibility with robot consistency. In service sectors, we might see robotic assistants, delivery robots, or increased use of drones for various tasks. For mechatronics engineers, this means opportunities to design robots that are safer, more adaptive, and more user-friendly. It also means focusing on things like human-machine interfaces, making sure humans can easily interact with and control these robots. There's also a push in robotics for improved mobility, like better walking robots, and dexterity, such as robot hands that can manipulate objects as skillfully as a human hand. These challenges are being tackled with mechatronic design and enhanced by AI and better sensors. Green technology and sustainability. Another future direction is applying mechatronics to solve environmental and energy challenges. For instance, designing smart grids for electricity. Those are mechatronic systems that manage power distribution using sensors and automated controls. Or creating robots for environmental monitoring and cleanup. Imagine a robot fish that can detect pollutants in water and help filter them out. Electric vehicles and renewable energy systems, like automated solar trackers or wind turbines with active control to maximize efficiency, rely on mechatronics to function optimally. As the world focuses more on sustainability, mechatronics provides tools to create cleaner and more efficient technologies. All these trends point to one thing: mechatronics is a field with a dynamic future. The integration of AI, connectivity, and advanced computing with mechanical systems means the machines of the future will be even more capable and interconnected. Mechatronics engineers will be at the forefront of building everything from smart wearable health devices to intelligent robots that could work in our homes. It's an exciting time to be in this field, as innovations in sensors, computing power, and materials open up possibilities we could only dream of a few decades ago. Conclusion. To wrap it up, mechatronics engineering is all about bringing different technologies together to make smarter machines. From its origins as a marriage between mechanical and electronic engineering, it has grown into a broad discipline that touches almost every aspect of modern life: our cars, our hospitals, our homes, our factories, and likely even the devices you're using to watch this video. The beauty of mechatronics is that it's inherently multidisciplinary and creative. One day you might be solving a mechanical problem, the next day writing code, and the day after analyzing data from a prototype. For those of you interested in learning or possibly pursuing mechatronics, know that it's a highly rewarding field. It can be challenging because you have to understand a bit of everything, but that also means it never gets boring. And as we've discussed, the career opportunities are robust and growing. Industries are looking for engineers who can bridge the mechanical and digital worlds, who can design a robot or smart device from the ground up. If you're someone who loves gadgets, robots, or just figuring out how things work and making them better with tech, mechatronics might just be the perfect field for you. Thank you for joining this exploration of mechatronics engineering. We've covered how it works, seen it in action in various fields, and peered into what's coming next. Hopefully, you've gained a clearer understanding of what mechatronics is and why it's so important in today's technology-driven era. Stay curious, keep innovating, and until next time, thanks for watching.